How to explain the equation 6-6. So we can begin with the radioactive decay equation, Nt equals N0 exponential minus lambda t. We know that our number of strontium 87 is equal to the quantity that was at the beginning plus the quantity that is decayed by rubidium 87. So we can just put it in a simple equation like our strontium 87 is equal to the strontium at the beginning plus the rubidium at the beginning minus the rubidium now, which has been decayed in strontium 87. By using our radioactive decay equation, we know that our rubidium at our time right now it is equal to the rubidium at time 0 times exponential minus lambda t. So we can, by just making a little bit of calculation, we can find the substitute for rubidium 0. Using what we found, we can inject it in our formula to get rid of our unknown, that is the quantity of rubidium at time 0. After doing this, we can just divide everything by strontium 86. And we can see that here we have done a little bit of merging I just wanted to describe this step. And we find the same formula, which is in the form of y equal ax plus b, which is a straight line. So we're going to complete this little table by just making simple calculation. If there is a 5% decay of rubidium, we take the time 0 rubidium times 0.95 and we have what it lasts after 5% decay, the same for 10. And then we add what we missed in rubidium, we add it to strontium. And we can see that strontium 86 is a constant. So it can be useful to divide it by this constant to see how the relationship between the variation of strontium 87 and strontium 86. So we can do it for all our minerals, and then we can plot an isochron diagram. We can see that it's very similar to what we had on our textbook. And then how to derive age, we can use our newfound slope. We have all the elements of our equation. We just missed the value of time, and we have to resolve it with what we can see on the graphics.
Can you explain the figure 3 again? X 轴跟 Y 轴.
At the left-hand side, you have the original raw data. What are the data you extracted for plotting the figure? Can you specify the original data in the left table?
I just went to the notebook. I saw that our value for X was rubidium 87 on strontium 86 and strontium 87 on strontium 86. So I went to my table and I just selected on each slope, it was the value of the different minerals, like 3 values. Plug light, I went to time 0 and I took this one for X, this one for Y. I made it each time. I selected it manually so I can plot my thing. And I've done the same thing for the 5% decay and 10% decay.
How do you draw the isochron diagram? I want to know what data you choose.
I first recognized what data I should extract from the table. I made it in a simple table. Then I went here. I've done like control and then select for the X, and then select for the Y, and I've done it 3 times for all my data. For 5% decay, I've chosen this one, then control this one for X. And then I've chosen this one, and this one for Y.
You see, at the very last step, scientists divided everything by strontium 86. Do you have any idea why they want to do that?
Because I think that is the 86 SR will not decay, so the amount of the element will not decrease or increase. That is unchanged.
Stable isotope. That's what you mean, right? Then my next question is, there are so many stable isotopes. For example, why can't they divide everything by silicon?
Because there is a similarity in the number of strontium 86 atoms in our minerals. If we divide by strontium, we have values that are more readable. As we can see on our isochron, we are between 0.6 and 0.8. It makes everything like simpler, maybe.
That was a very good guess and good argument, but that is not the real answer. But I appreciate your ability to make arguments. Very good. Thank you. I know in our department, if you like mathematics, you will go to physical oceanography lab. If you don't hate mathematics, but you don't like it either, you probably go to geology or chemistry lab. And if you hate mathematics a lot, you probably go to biology lab. However, my suggestion is try to give yourself a chance to get to know mathematics. It might be a cliche, but mathematics is indeed your friend. It's a tool and it's a friend. That's the reason why in my course I always add a little bit mathematics so that you can get some first-hand experience how people really handle their data. Even if you are at the biology division, you still need to learn statistics. I heard that this year there are only 10 students subscribing to that course, Apply Statistics. I was totally surprised because to me, statistics is the most useful mathematics tools, basically for every discipline. If you want to go to graduate school, I can't even imagine without statistic concepts how you can work on your master thesis project. I know looking at these Excel spreadsheet or equations make you feel headaches, but if you try to sit down, calm down, drink some coffee, and then try to work it out, when you figure out that you can work it out, this feeling of achievement is, you feel that you have a very powerful tool in your hand. I really want to encourage you to get in touch with mathematics. It's your friend. We want to talk about radioisotope geochemistry. When we need to talk about radioisotope, there's always calculation. Before we enter the deep water zone, I want to give you some poetic account regarding geological time. There are two phrases that we often cite. The first is, the mind seemed to grow giddy by looking so far into the abyss of time. When you think about how ancient, how old the earth is, you feel dizzy because it's so long time ago. The second phrase is, no vestige of a beginning and no prospect of an end. That is also a description of geological time. These guys, they were before the discovery of radioisotope. So now we know there was a beginning, right? Big Bang. We try to pinpoint the events that happened in the past, so we know what went on and what is going to happen in the future. That's the work of dating. Before dating, we need to talk about the discovery of radioactive decay. That was in late 19th century when Röntgen discovered X-rays. 1 year later, Henry Becquerel found that uranium compounds spontaneously emit energy that possess penetrating properties like X-ray. Because of this discovery, Henry Becquerel, his name BQ, is the standard unit of radioactivity. In your next assignment, you will use this unit, BQ. That's a unit for radioactivity. 2 years later, Marie Curie called this spontaneous emission of energy radioactivity. She and her husband suggested that some subatomic particles might be unstable. So far, everything is only in physics or chemistry. This has not been applied to geological material. it's important to know there is radioactivity in Earth's material because these radioactive material, they are the source of heat. We know in the interior of the Earth, it is very hot. Why is it very hot? Because there is radioactive decay. And the second is, these radioactive nuclei, they act as an absolute timekeeper. That's how we get to know the order of things that have happened in the past. Radioactive decay. I guess I don't need to repeat this. Half-life. After a certain amount of time, half of the parent is gone. So we usually call parent and daughter. I don't know why they don't call parent and son. You have seen this chart of nuclei. You know there are at least two kinds of decay. Alpha decay, which is the loss of helium-4. Beta decay, which is a neutron decomposed to proton and electron. And there is also the inverse of beta decay, which is electron capture. Each of these, there is associated dating technique. Decay equation. I think Axel started from here. In his presentation, he cited this equation. However, this equation originated from a more fundamental chemical equation, which is first-order reaction kinetics. This is the most common kinetics in nature. And this is not limited to radioactivity. It actually applies to many, many chemical reactions. If you read this, you just read it as D, okay? I think this is better. Have you seen this before? No? If you read it in plain language, that means C is concentration. Delta C divided by delta T, that means the change of concentration over time. That means rate, reaction rate. Reaction rate is related to concentration. The higher the concentration is, the faster the reaction rate will be. That's the explanation of this equation. And K is a reaction-specific constant. So every reaction has its own constant. So that's the first-order reaction kinetics. It's related to concentration. There is another often seen kinetics. Zero order, which means the reaction rate is constant. The left one means it's constant. The right one means it's not constant. It will change depending on the concentration of the reactant. And this equation can be derived from this one. Here you will see some mathematical derivation. You take the A here, which will be here. You take the delta T here, which will be here. Then you do integration from time 0 to t. Recall your calculus course. The integration of the inverse of x is equal to natural log x. Then you apply this to this integration. You will get this. You will start to see natural log because it comes from this general principle. Then you recast the whole equation. It will get you this one. That's how you derive this equation from the first-order reaction kinetics. Half-life. Half-life, by mathematical definition, is the amount of concentration is only half of the original. So it's 0.5. You can put this relationship into this equation. Then you get this one. Then you recast the whole equation. You get this one. T is the half-life. Is natural log 2 divided by lambda. This is half-life. This is lambda. Why I emphasize this? Because this is needed for your next assignment. And this is radioactive decay. This is the number of half-lives, and this is the number of atom. The black one is parent, and the gray one is daughter. You have to pay attention that this is a logarithmic scale, not linear scale. If you plot them at the linear scale, this one is linear scale, their behavior or their change over time is not linear. that would fit the radioactivity decay equation better. Both the decrease in parent or the increase in daughter is not linear. Now I have a question. What is the percentage of the original parent radioisotope left after 10 half-lives?
大概1/1000。
About 1 per mil, okay? That would be the percentage of the original parent. Only 1 per mil is left. Therefore, we usually say the utility of a radioactive isotope is limited to 10 half-lives. This is an important number for people who want to use dating technique. For example, the half-life of lead-210 is 22 years. What is the utility of lead-210? 220 years. The half-life of carbon-14 is about 5,000 years. Then the utility of C14 is about 50,000 years. If you want to talk about last glacial period, that is about 10,000 years ago, you can comfortably use C14, which has a utility of about 50,000 years. However, you cannot use lead-210, which has a utility of only 220 years. That's how you tell which dating technique you should use. There is another simple mathematics. A radioactive isotope has the following abundances over time. 10 million years ago, it has 10,000 atoms. 9 million years ago, 8,000. 8 million years ago, 5,000, and so on and so on. What is the half-life?
Half-life is 2 million years.
How do you know that?
但它变成一半，就是从10 million 到8 million。
Very good. That's how you identify its half-life. These are the useful decay schemes, which means the method that geologists usually use. Because in nature, there are so many different isotope pairs. You may wonder, which one should I use? Here are a few that we usually use. C14. This is its half-life. In a few weeks, we will talk about potassium-40. This method is used to date volcanic rock. In your assignment, you use rubidium, strontium isotope pairs. These are used to date super old material, like meteorite. Here are a few other dating schemes, but we will not talk about them during this lecture. In this lecture, we will only talk about potassium, argon, rubidium, strontium, and C14. And of course, we talk about lead-210, but it's not here. Go back to the dating equation again. The activity at a certain time is equal to, so you move this A0 here, is equal to the activity at the beginning times the exponential minus lambda t. So you have to think practically. What do we need to know in order to know t, and how? AT, that means the activity at the time you measure the sample. Then this is no problem because you have the sample, so you can measure it by mass spectrometric analysis. So this one has no problem. Lambda is the decay constant. And this one is also okay. You might say, yeah, we can look it up at Wikipedia, then we know what is lambda. But then you must ask, how do previous people know lambda? Apparently, this is something that needs to be measured. You need to measure it using physiochemical analysis. What does that mean? I guess you must have heard some story like some scientists or some Iranian. They want to concentrate radioactive isotope. But apparently scientists and Iranian, they have different purpose. For scientists, the reason why they want to concentrate radioactive isotope is, if you recall, A is equal to lambda times n. If your half-life is very long, that means your lambda is very small, right? Then it's difficult to measure A. How to solve this problem? Very easy, you increase n. That's the reason why you want to concentrate it. The more concentrate isotope you get, the easier and more accurate you will get for lambda because you measure this. Apparently, this is your obstacle. You don't know this. You cannot go back to the past, get a sample, and bring back to the future and say, I want to measure it. No, you can't do that. That's the time point when we need to talk about the general requirements of radioactive isotope dating. First of all, the sample you use for dating has to be a closed system. Dating materials do not have exchange of isotope or elements with the surrounding. Take carbon-14, for example. When I am alive, am I a closed system? No, because I'm still breathing, I'm still eating, peeing, pooing. Therefore, my C14 is constantly changing. However, if today I died, then I am a closed system. If I'm buried in soil and maybe 5,000 years later, some archaeologists, they can use my dead body for dating because it's already a closed system. And you need to know the decay rate constant, which, as I said, has been measured by some physicists. So this is not the issue for people who apply the technique. This is usually known. And then what is usually not known is, this one is usually not known. Then you might hope that one of these two conditions would stand. One is initial concentration of daughter is known. If you know the initial concentration of the daughter, if the daughter you measure today is different from the initial concentration that you know, then you will know that all the daughter comes from the parent. Then in a way, you know A0. The best would be for this material, the initial daughter concentration is 0. You might ask, is there any case like that? Yes, zircon. 它可以做铀铅定年。锆石这种矿物，它在结晶的时候，它会自然的排除铅。这个就是我们讲的初始的女儿的含量是知道的。那通常知道就是指0。这个通常是怎么形成的？就是看这个矿物本身在结晶的时候，它会天然的去排除某些元素。That's a first condition. If this condition cannot be met, another good thing is you know the initial concentration of parent, which means you know this automatically. Which case is this? The answer is carbon-14. Because carbon-14 is being produced every day, because it is produced by cosmic ray every day. Scientists assume that the flux of C14 today is the same as yesterday, or 1,000 years ago, or 10,000 years ago. That's what we said. Initial concentration of parent is known. So you know there are really cases that fit this condition or this condition. However, we know there are so many different kinds of dating techniques. How realistic are these requirements? The answer is most of them will not fit these two requirements. Their initial concentration of parent and daughters are not known. How do I do the dating? How do I solve the question? That's the genius thing about isochrone, because with the isochrone technique, you do not need to know the initial concentration of parent and daughter, but still you can date. That's how genius it is. You already know from your assignment for the isochrone, we use the rubidium strontium system. It has a very long half-life. Strontium 87 is the daughter in this isotope pair. However, we do not know its initial concentration. This technique can be used to analyze meteorite. In meteorite, once it is formed, there is already some strontium 87. We don't know how much it is. Neither do we know the initial amount of rubidium 87. Then genius says, let's use isochrone. You know this equation, you know how to derive it. The initial equation is like this. This is measured today, this is measured today, but these two are unknown. With this equation and substituting with some rearrangement, you end up with this. Now, this one is the only one that's unknown. This unknown is removed. You still have this unknown. Is that a problem for you? No, because you use this y is equal to b plus mx. this linear equation. This is known because this is all measured. This is also known. Here you have unknown, but is that a problem for you? No. For the time, it is at the slope. Therefore, you can easily solve this without having to know this. That's the most genius part of this transformation. Why do you have to divide equation 8 all by strontium 86? Strontium 86 is a stable isotope, and its quantity does not change over time. Can I substitute strontium 86 by C12? No, you can't do that. This is because the so-called the trick of ratio. In mass spectrometry, ratios are more accurately measured than absolute amount. So that's the reason you want to divide it by strontium 86 so you can get very precise measurements by mass spectrometry. Can I use another stable isotope? The answer is no, because you want to make sure that the mass you measured is close to each other. 87 and carbon 12, their mass is very different. Therefore, in mass spectrometric analysis, you cannot get very precise measurement. That's the reason you want to choose something that has very close mass to your target isotope. That's the reason they choose strontium 86. Talking about this, I would like to bring you back to our introduction lecture where I asked you, what would you do with these data sets? Okay, and some of you said you will calculate average. The other said maybe you will look at time series. One of you said you will do correlation. In fact, linear correlation is the spirit of geochemistry. In geochemistry, many data manipulation will transform to this form. When you do this, you can use all of your measurements to determine one value. The X and Y here means many different measurements. And then you use all these measurements to solve one value. This technique is used many, many times. Isochrone approach, how it works. So in a meteorite, the strontium 87 and strontium 86 ratio, so this ratio means the time zero ratio of different minerals should be the same if they come from the same interstellar material and have mixed well. However, some minerals have more rubidium at time zero and therefore have higher rubidium 87 to strontium 86 ratio than others. In a meteorite, there are many, many different minerals. At time zero, their strontium 87 to 86 ratio of these different minerals should be the same. But the rubidium to strontium ratio should be different. Okay, my question is, why? This is related to a very important concept that I have told you in the lecture, mineral chemistry. To give you some hint, you can just focus on the second point. Why do different minerals have different rubidium to strontium ratio?
I guess, but probably because these minerals 生成环境不一样之类的，就是它们在地质里面发生的作用也不一样。
They are all formed from the same interstellar material in the space. The answer is have you seen this before? Isomorphous substitution. I think when I talk about isomorphous substitution, I told you this is a very important phenomenon. And actually, for many of the geochemical application, we make use of this. What is the definition of isomorphous substitution?
According to internet, silica is replaced by an aluminum in a mineral.
And what is required for this replacement to happen?
相似的离子半径，像铝、锰、镁，铝三正，然后锰二正，然后镁二正，它们的那个离子半径会一样，所以呢就可以发生同型替换。
Very good. Comparable size, comparable charge. So why do different minerals have different rubidium? When I say rubidium here, I did not limit it to rubidium 87. I mean all rubidium. This is related to the rubidium ion itself. And different mineral, they have different structure. Therefore, they can allow different level of rubidium substitution. You might ask, does this also apply to strontium? Yes. They will also have different strontium content. Then you may ask, but why do you say this ratio will be the same? This is because when isomorphic substitution happens, it does not differentiate different isotope. It only differentiates based on its radius and charge. For strontium 87 and strontium 86, for mineral, they are all strontium. So their level of isomorphic substitution will be the same. That's the reason why this ratio will be kept the same for different minerals, while these different minerals may have different strontium content and also different rubidium content. As a consequence, the difference in strontium 87 to 86 ratio will increase over time because this one is stable and it will not be produced by another radioactive isotope, but this one will be produced by rubidium 87, so it will increase over time. And the key point for the isochrone approach is, as your assignment show you, you need to find at least 2 different minerals. I think 2 is too few. You need to find at least 3 different minerals, and these 3 minerals, they should have different rubidium content so that you can really draw a line. You can obtain the slope. So the slope is what we want. You know this very well, so I will skip this. Very important, 3 different minerals. Results from minerals of a chondritic meteorite samples. This is the result of a chondritic meteorite samples. You can see in this sample, they measure many different mineral grains, and they sit very well on this line. This line tells you the time is 4.56 billion years ago. Because this is chondritic meteorite sample, chondritic meteorite sample has the same relative composition as the sun. Therefore, this material is considered the best representative of pristine solar system material. Therefore, its age can represent the age of the solar system. Key point, why can't we use rocks collected from different parts of the Earth to do this? These are all from a chondritic meteorite. Can we use the rock on Earth to measure this?
应该不行吧？有熔融过吗？
Oh, very good. Because the rock has been melted. On Earth, we have plate tectonics. And within plate tectonics, the rock has been recycled. Every time it is melted, the rock will become an open system again. This will violate our requirements that the dating material has to be a closed system. That's the reason we cannot use the rock of the Earth to date the solar system. And these are just some results showing many different meteorites. And their dating results are all around 4.55 billion years ago. Therefore, this age is robust. Furthermore, some people use different isotope pairs, and they also get the same results. So this result is very, very robust. Next week, we are going to talk about uranium series. People start to get really scared about this because there are too many isotopes. A student, A here means activity. the activity of polonium-210 and the activity of lead-210, their ratio is 1 in natural system. A is activity in becquerel per unit volume or weight. It's radioactivity, so it's in becquerel. This is not a coincidence. This means the ratio is 1. This is not a coincidence, but a consequence of secular equilibrium. 永视平衡 in Chinese. Their ratio will always be 1. Use the example in spreadsheet A here to understand the concept of secular equilibrium. Calculate this ratio with a time step of 0.25 year. What I am asking you to do is a chemical modeling. It's a very simple chemical modeling. Hint, you need to use this equation. I already tell you which equation you should use. So second, A is radioactivity. It's equal to lambda times N. N is the number of atoms, and lambda is the decay constant. Then, to answer this expression, you need to use the Excel function like exponential, EXP. Let's look at this. So this is what we need for chemical modeling. We need to have prescribed initial condition. This is lead-210. This is polonium-210. Here I tell you their initial number of atoms in seawater. The unit is atom per cubic meter seawater. You need to look up from the internet their half-life. If you don't know how to look it up, you need to check my previous video recording. From the half-life, you can calculate its decay constant using this. That's how you calculate from half-life to decay constant. After this, you can calculate the number in seawater, the activity in seawater for lead-210 and polonium-210, and then you can calculate their ratio, activity ratio. You need to keep in mind that N and A, they are different. They follow this equation. Afterwards, you should draw a figure showing how this ratio change over time. You will see this ratio change over time. Answer the following question. How long does it take for the isotope pair to reach the secular equilibrium? It means how long does it take for this ratio to reach 1? Second, how can researchers make use of the secular equilibrium between isotope pairs? This is of utmost important property of uranium series. The second part is for your own imagination, how this relationship can be used. In spreadsheet B is the raw data of lead-210 EX. This means excess lead-210. Lead-210 measurement from a sediment core. Lead-210 is the most commonly used dating technique for marine sediment. And this is a real data. Here you see it's a very short sediment core. I slice the sediment into 2 centimeter slices, and this is the mid depth of each slice. And this is the excess lead-210 value. Use the data to calculate the sedimentation rate in centimeter per year. You need to read chapter 6 for data processing. Do not use calculator, compute only in Excel. You need to draw graphs. You use Excel functions like a natural log and slope in order to solve the sedimentation rate from this data. Solve this question graphically. That usually means you need to do linear regression, find answer in either at the slope or the intercept of the linear regression. That's my hint. This technique is very important because nowadays we want to talk about carbon burial. We want to study peat, wetland. We want to know how rapid the carbon is getting buried. When you want to answer questions like this, you need to know the sedimentation rate. And lead-210 is the most commonly used technique to calculate sedimentation rate.
Just what does dpm per G means?
I should change this to becquerel.
Okay.
It's becquerel.